The probability you clicked on this video is 100%. The probability you will watch the entire video, well, that's for you to decide. But today we're talking about probability. So, the basics of probability. What is probability? Probability is the chance of something happening, and it can be calculated by finding the number of desired outcomes or successful outcomes divided by all of the possible outcomes. For example, the probability of rolling a multiple of 3 on a 6-sided dice, well, how many successful outcomes are there? 3 or 6, so 2 successful outcomes. How many possible outcomes are there? 6 choices for a dice, so our answer is just 2/6 or 1/3. Now obviously that was a very simple example, but let's explore some more interesting problems. What is a probability that the product of 4 dice rolls is a multiple of 648? Four dice rolls product is 648. What is 648? Well, we should try to find the prime factorization for 648 because we don't really know what it means to be a multiple of 648 until we find its prime factorization. 648 is 2 times 324, which is 2 squared times 162, or 2 cubed times 81. And 81 is just 3 to the 4th power. So 648 is 2 cubed times 3 to the 4th. So we've got 4 dice rolls, and the product has to have 3 multiples of 2 and 4 multiples of 3. Okay, so 4 multiples of 3. Wait. So each dice roll is 1 through 6, right? And there's no way there's more than one factor of 3 in the dice roll. If we have 3, that's one factor of 3. If we have a 6, that's also one factor of 3. Everything else, that's 0 factors of 3. And a 9 is not possible. So, therefore, the only way for a number to be multiple of 3 is 3 or 6. Oh, but the product of all 4 numbers is 3 to the 4. So is it even possible to have a number that's not divisible by 3 as one of our dice rolls? No, actually. Why? Because if any one of these 4 numbers that are rolled from the dice are not a multiple of 3, then the product will not be a multiple of 3 to the 4. Because each one of these dice rolls can be either a multiple of 3 or a multiple of, or not a multiple of 3. Nothing can be a multiple of 3 squared or more. So if all 4 numbers product must be multiple of 3 to the 4, every number must be a multiple of 3. So we can mark 3, all the multiples of 3. Okay, but we've also got this condition that it has to be a multiple of 2 cubed. Oh, so we know each dice roll is 3 or 6, and 2 cubed. So the dice roll that we narrowed down by this condition over here is that it's either just 3 or 2 times 3. So either we just get a factor of 3, or we get a factor of 3 and a factor of 2. Okay, so we need at least 3 factors of 2. So what happens if we have 0? So each one of these adds an extra factor of 2, essentially. So we must have 3 of these 6s, right? We've already narrowed down each dice roll must be a 3 or a 6. And each one of these 6s gets an extra factor of 2. And we need 3 of them. So we need at least 3 6s. So we can have 3 6s and a 3, or all 4 can also be 6s as well. Because if all 4 of them are 6s, then the product will be a multiple of 2 to the 4, which is 16, which is a multiple of 8 indeed. Okay, so now we're looking for probability. So let's find successful outcomes divided by total outcomes. Successful outcomes such that this probability, this multiple is true. How many ways are there to roll 3 6s and a 3? Well, there's just 4 ways. We've got 4 slots essentially, and one of them must be a 3. What about over here? We have 4 6s, so just one. I mean, there's only one way to have 4 6s in a line. So 4 and a 1. Okay, there's a total of 5 cases, as you can see here, right? 5 cases in total give so that the product is a multiple of 6, 4, 8. And how many total cases are there? Each dice roll has 6 choices. So 6 times 6 times 6 times 6. That's 6 to the power of 4. And 6 to the power of 4, you can multiply it if you'd like, but it can be good to memorize. This is just 1296. So this is our answer over here. And you can get these written examples in the free Mastering AMC 8 book, link in the description. Let's take another cool example with dice rolls and probability. Person A rolls a dice with the numbers 1, 1, 2, 6, 15, 30. Person B rolls a dice with the numbers 1, 2, 4, 18, 28, 28, 44. What's the probability? The product of the two dice is a multiple of 24. 24 equals 2 cubed times 3. So, for the numbers to have a product that's a multiple of 24, we must have 3 factors of 2. Let's look at person A. 3 factors of 2. So the product of these two dice must have 3 factors of 2. Let's take a look at how many factors of 2 the numbers have. So for person A, 1 has 0 factors of 2. 1 has 0 factors of 2. 2 has 1 factor of 2. 6 has 1 factor of 2. 15 does not have any factors of 2. And 30 has 1 factor of 2. For dice B, 0 factors of 2, 1 factor of 2, 2 factors of 2, 1 factor of 2, 2 factors of 2 because 4 times 7, and 2 factors of 2 because 4 times 11. In total, the product must have 3 factors of 2. But if you look here, the maximum number of factors of 2 from the second dice is 2, right? We can't have 0. The maximum, we can't have 3 factors of 2 for just person B's dice. So 2 factors of 2 is the maximum for person B's dice roll. And for person A's dice roll, 1 factor of 2 is the maximum. Oh, but we need 3 factors of 2 total, the product. So 3 factors of 2 total means that we must have the maximum number of factors of 2 possible. We must have the 4, the 28, or the 44 for person B, right? We must have one of these 3 dice because they all have 2 factors of 2. And for person A, we must have 2, 6, or 30, right? Because this is the maximum number of possible factors of 2 for the product is 2 to the 1 times 2 squared, which is 2 cubed. So we must have the maximum, because anything less won't be a multiple of 2 cubed. Okay, but it also has to be a multiple of 3, the product. Let's take a look at which of these cases. We've already narrowed it down a lot, so we've got very few cases left to check. Person B, are any of these multiples of 3? Nope. 4 isn't, 28 isn't, and 44 isn't. What about A? Which one of these are multiples of 3? 2, of course, isn't, but 6 and 30 are. So for the product to be a multiple of 3, at least one of these numbers must be a multiple of 3. So if person A chose 2, there's no way person A times person B will be a multiple of 3, because B has no numbers that are a multiple of 3. So therefore, person A must choose 6 or 30, because 6 and 30 are multiples of 3. So when you multiply by person B's number, it will become a multiple of 3. Okay, so these are all the cases that work. How many are there? 2 choices for the first case and 3 for the second case. They all, person A, if you multiply them all out, they'll both have, all of these cases will have 3 factors of 2 and 1 of 3, at least. So 2 times 3 equals 6 successful cases. Now, how many total cases are possible? That's just going to be 6 times 6. 6 choices for each of the 2 dice rolls. So then it's just 6 over 36, which is 1/6. The probability, 1/6. So to summarize, we first broke 24 into 2 cubed times 3. Then we saw, oh, for it to be a multiple of 2 cubed, we must have 2 factors of 2 for B and 1 factor of 2 for A. And then we saw that 6 of these cases had the product being a multiple of 3, because we must choose 6 or 30 for A for it to be a multiple of 3. So 6 over 36, 1/6 is our answer, our probability. Let's come back to this. And so that was essentially the probability of independent events, essentially, because the events were independent of each other. So to find it, we just simply find the probability of each event individually happening. So the probability of A having a multiple of 2 and B having a multiple of 4, and of course A also having a multiple of 3, essentially. This was independent events because dice A and dice B were independent of each other. But that's not always the case. In dependent events, we say the events are dependent if the probability of both events happening, basically if we have two events, they're dependent. To find the probability, we just find the probability of event A happening times the probability event B happens, given that event A already happened. Now, let's explore what this means with an example. On Saturday, there is a 20% chance of rain. On Sunday, there is a 30% chance of rain if it rained on Saturday, but only a 10% chance of rain if it didn't rain on Saturday. As you can see here, they're dependent because whether it rains on Sunday is dependent on whether it rained on Saturday. What's the probability it will rain on both days or neither day? So what if it does rain on Saturday? There's a 20% chance of that happening. What's the probability it will also rain on Sunday? 30%. So 20% times 30%. This is just 3/10 of 20%, which is 6%. Right? This is the probability it will rain on both days. Underline this with this color. Now, what's the probability it will rain on neither day? 80% chance it does not rain on Saturday, and if it does not rain on Saturday, there's a 90% chance it won't rain on Sunday, right? Because if it does not rain on Saturday, there's only a 10% chance it will rain on Sunday. So there's a 90% chance it won't rain on Sunday. 80% times 90% is just 9/10 of 80%, right? Because 90% is 9/10, and this is just 72%. We add them up, we get 78%, and that's our answer. This basically was a simple demonstration of this thing that seems complicated, but once we have an example, it's more simple to understand that probability of A times event B happening, assuming that A already happened, which was these two terms in this problem. There's a 40% chance of rain on Saturday and a 30% chance of rain on Sunday. However, it is twice as likely to rain on Sunday if it rains on Saturday than if it does not rain on Saturday. Okay, now you might be confused. 30% chance rain on Sunday, but then if it rains on, but there's a twice as likely chance to rain on Sunday if it rains on Saturday. Wait, how is that even possible, right? After all, it says 30% chance of rain on Sunday. The key thing here is that this is the overall probability. It's the overall probability. So, because it's the overall probability, it does not necessarily mean that if it does rain on Saturday, there's going to be a 30% chance of rain on Sunday. And if it doesn't rain on Saturday, there's a 30% chance of rain on Sunday. This is just the overall percentage. That's all. So let's essentially take, but we were given this condition. It is twice as likely to rain on Saturday or on Sunday if it rains on Saturday than if it does not rain on Saturday. So in the 40% chance it does rain on Sat, there's going to be a twice as likely chance of raining on Sunday. So let's say 2x% chance on Sunday. And 60% chance it does not rain on Saturday, so no Sat. Then there's going to be just an x% chance of rain on Sunday. The probability it rains at least one day this weekend is A over B. And we're asked to find this quantity over here. So we haven't yet used this condition that 30% chance of rain on Sunday. But like I said earlier, that doesn't mean that there's always a 30% chance of rain on Sunday. That's just the overall probability. And what is the overall probability over here that it rains on Sunday? In the 40% chance, or 2/5 chance, it rained on Saturday, there's a 2x% chance of raining on Sunday. And in the 3/5 chance there's no rain on Saturday, there's an x% chance of raining on Sunday. Overall, if we add these up, we get 7x over 5% chance of raining on Sunday. Overall chance, right? And this is equal to 30%. It's given in the problem. So x, therefore we can remove the percent sign. 7x over 5 equals 30. So x equals 5/7 times 30, 150 over 7. So x is 150 over 7. And therefore, this is 150 over 7%. And this is 300 over 7%. So the probability it rains at least one day this weekend. At least one day this weekend. How should we do that? Okay, so it's asking for only at least one day this weekend, not in general. First of all, maybe we should not write 150 over 7 in percent form because we're going to have to deal with fractions anyway. So 150 over 7, let's convert it out of percentage. 150 over 7% is 150 over 700. You can cancel out a 0. It gives us 3 over 14. So there's a 3 over 14 chance it rains on Sunday if it did not rain on Saturday, and a 6 over 14 chance, just times 2, right? It rains on Sunday if it did rain on Saturday. Okay, so now we should just be able to, now let's just add up to find the probability it rains at least one day this weekend. Let's say it rains on Saturday. If it rains on Saturday, what's the probability it will rain at least one day this weekend? That's guaranteed. It's guaranteed because if it rains on Saturday, then it definitely rained at least one day this weekend because Saturday is a day of the weekend. But what if it did not rain on Saturday? Then there's a 3/14 chance it will rain on Sunday. So therefore, if it did not rain on Saturday, it must rain on Sunday to rain at least one day this weekend. So now all we have to do is add up these percentages. That's 40% plus 60% times 3 over 14. Well, that is just going to be equal to 40% plus 60% times 3 over 14. That's 3/5 times 3 over 14. And 40% is just 2/5. So the question is not asking in terms of percent, it's asking just in terms of probability. So let's convert from percentage to not percentage. So this becomes 2/5. Well, 2/5 is equal to 28 over 70, right? Because times 14 times 14. And the next quantity is 9 over 70. So overall, it's 37 over 70. Therefore, because 37 over 70 is our probability, and it says A over B, find A plus B, so 37 plus 70 is 107. And this is going to be our answer for this problem. The key idea was seeing if it did rain on Saturday, what's the chance of raining on Sunday? And if it didn't, what's the chance? Then we solved our equation, got the value, find the probabilities, and then we just see that if it did rain on Saturday, it's 1 guaranteed to rain at least one day. And if it didn't, then there's a 3/14 chance if it did rain on Sunday. And we get 107. Okay, now let's go back to this problem over here. Mark must choose a seat from the 5x5 grid of chairs in the classroom. His enemy, Steve, does not like Mark, so wants to choose a seat that is not in the same row or column as Mark. However, to his dismay, the teacher randomly assigns seats. What's the probability that Steve is not sitting in the same row or column as Mark? 5 by 5 grid of chairs. Now, let's draw that out here. 5 by 5 grid of chairs. Basically, we're asked to find the probability that Steve doesn't sit in the same row or column as Mark. So, this is like a good review. Is this dependent or independent? Is Mark's probability dependent on or is Steve's probability dependent on where Mark sits, or is it independent on where Mark sits? That's kind of the key thing to try to figure out here. So where does Mark sit? Let's say Mark sits here. Okay? Mark sits there. Now, where can Steve sit? First of all, Steve can sit anywhere else. There's a total of 25. 5 times 5 is 25 seats. So therefore, there's 24 remaining seats for Steve to sit in. 5 times 5 minus 1. So this is the total number of outcomes in the probability equation. Now, how many of these outcomes have Steve not sitting in the same row or column as Mark? He's randomly assigned, so he could be sitting anywhere. But what's the probability? He's not in the same row or column. In this case, for example, Steve can't sit here because of the column, and he also can't sit here, 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 or here because of the row. Now, if we count them, there's 1, 2, 3, 4, 5, 6, 7, 8 additional seats that don't work. So out of the 24 options, 16 work. So if Mark sits here, for example, the probability is 16 over 24, which simplifies to 2/3. Okay. What if Mark sits somewhere else? So 16 over 24 equals 2/3 if Mark sits over here. What if instead Mark sits over here in the center? Again, Steve can't sit here, 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 or here, or here, or here. Again, it's 4 in the column where Steve can't sit, and 4 in the row where Steve can't sit. Again, 8 cases don't work. Again, the probability is 16 over 24 equals 2/3. This is seeming a little suspicious. Is it always 2/3? Let's see. Oh, so wherever Mark sits, it doesn't even matter. There's five squares in a column, so Steve can't sit at any of the other 4 squares in the column. Similarly, there's 5 squares in a row, so Steve can't sit in any of the 4 squares in the row. So in total, out of the 24 possible seats, 8 will always not work, regardless of where Mark sits. So the probability is always 16 over 24 equals 2/3. So it's independent. It's independent probabilities. Even though it may seem dependent, Mark is Steve, it should depend on where, intuitively, it seems like it should depend on where Mark sits, right? But it doesn't. So the probabilities are independent. And the answer, just 2/3. And that's a brilliant way. Okay, let's move on to another topic in combinatorics, which is casework. Casework is where general strategies like combinations, permutations, they aren't enough because there's not just one thing you're counting now. You have to break a complex problem into cases and find each of those cases separately. Let's explore that over there. Click on it right there.